Hello everyone. In this lesson, we will study the temperature strain curve of low crystallinity polymers. Learning objectives: be able to theoretically guide the synthesis of low crystallinity high molecular weight polymers with the correct molecular weight. Knowledge objectives: understand the specificity of the structure of crystalline polymers. Master the temperature strain curve of low molecular weight, low crystallinity polymers. Master the 4 states of high molecular weight, low crystallinity polymers. Quality objectives: learn to grasp the essence of things through logical analysis. Grasp the essence of things. As we all know, the temperature strain curve of crystalline polymers is unique. These polymers have both amorphous and crystalline regions. There is also a crystalline portion. For the amorphous portion, there are 3 states during temperature changes. This corresponds to 2 transitions. For the crystalline portion, as the temperature increases, a phase transition occurs. When the temperature reaches its melting point, it starts to melt. Polymers with different crystallinities exhibit different temperature strain curves. In general, the temperature strain curve and the mechanical state changes of crystalline polymers are much more complex than those of amorphous materials. Let's discuss high and low crystallinity polymers separately. First, let's look at the glassy state. Low crystallinity polymers have a glassy state. And within this glassy state, crystalline phases also exist. As the temperature increases, a glass transition occurs. In this transition region, we can determine its glass transition temperature. As the temperature rises further, it enters the second region. We call this state the leathery state. Why is this state called the leathery state? The temperature of the leathery state lies between the glass transition temperature and the melting point. This is because it is a high crystallinity material, therefore, it has a melting point. Having a melting point means there is a phase transition. At the same time, in polymer systems, both crystalline and amorphous phases coexist. In this system, some polymer chains are crystalline, others are amorphous, and others are not crystalline. These crystalline portions are relatively few. They are dispersed in the amorphous polymer matrix as microcrystals. So, when the temperature exceeds the glass transition temperature, the non-crystalline chain segments can move. However, the crystalline segments are still constrained by the crystal lattice and cannot move. These segments cannot move. Therefore, they restrict the movement of surrounding segments. From the whole system, it cannot move as freely as a completely amorphous elastomer. Its motion is restricted. At the same time, it is not as rigid as the glassy state, nor as elastic as the normal elastomeric state. The change is not as significant. Therefore, it is in a state between the two, resembling the leathery state. Thus, we call it the leathery state. As the temperature increases, we enter the third region. This reaches the melting point of the crystalline phase. The crystalline phase begins to melt. For this polymer, once it passes the melting point, all the chain segments can move. When the molecular weight is low, the melting point of the polymer coincides with its TF. That is to say, the melting point is greater than or equal to the viscous flow temperature. Once it melts, it immediately enters the viscous flow state. Therefore, the curve rises steeply. The strain increases significantly. After melting, it immediately enters the viscous flow state. Therefore, for low molecular weight polymers, looking at the curve, there are 2 transition temperatures. One is the glass transition temperature, and the other is the melting point, which is also the viscous flow temperature. For high molecular weight polymers, because of their high molecular weight, their viscous flow temperature is higher. The viscous flow temperature is higher than its melting point. For the same polymer with different molecular weights, they have the same structure, only the molecular weight differs. Therefore, their melting points are similar. However, for high molecular weight polymers, the viscous flow temperature is higher. After melting, it enters a normal elastomeric state. After melting, all the chain segments begin to move normally. Then, it enters the viscous flow state. Therefore, systems with high molecular weights are more complex. Their transition temperatures have 3 points: glass transition temperature, melting point, and TF viscous flow temperature. At the same time, their states are more varied. It has a glassy state, a leathery state, a normal elastomeric state. and a viscous flow state. In addition, high molecular weight, low crystallinity polymers have a higher high elastic state temperature, and the range is narrower. It has no practical use. It does not behave like the high elastic state of amorphous polymers. It has a relatively wide temperature range. If the room temperature is within the high elastic state range, it can be used to make rubber elastomers. However, for plastics, the high elasticity of crystalline plastics is of no practical use. Therefore, for low crystallinity high molecular weight polymers, the molecular weight is generally adjusted lower during synthesis to meet its melting point, so that the melting point coincides with the viscous flow temperature. In other words, its melting point is greater than or equal to the viscous flow temperature. This helps lower the processing temperature. In other words, it can be processed immediately after melting. There is no need to wait until it reaches the normal high elastic state and then enters the viscous flow state for processing. This reduces our energy consumption. The processing temperature of crystalline polymers is actually not related to the viscous flow temperature. It is only related to the melting point. Next, we will introduce the temperature strain curve of highly crystalline polymers. That is, polymers with crystallinity greater than 40%. The temperature strain curve of these polymers looks like this in the PPT. We still need to divide it into high and low molecular weight segments. First, for low molecular weight, we can see from the temperature strain curve, the glass transition of the amorphous portion is not observed. In other words, there is no Tg. It starts in the crystalline state. There is no glass transition. Why is there no glass transition? This is because its crystallinity is very high. In the entire polymer system, the crystalline region occupies much more space than the amorphous region. Most of the material is crystalline. This means that microcrystals are interconnected. The amorphous phase is very sparse. Moreover, its motion is significantly restricted. Therefore, the glass transition is not visible during measurement. Although it is not visible, it still exists. In other words, the glass transition still occurs. The amorphous chain segments are very few. Within the testing range of the temperature strain curve, or experiments such as thermomechanical analysis, it is generally difficult to measure. This requires instruments with very high sensitivity. The curve shows a clear Tm. After the Tm temperature, it is still divided into high and low molecular weight parts. For low molecular weight, highly crystalline polymer materials, its melting point is still greater than or equal to Tf. Similar to low crystallinity polymers, after melting, it immediately enters the viscous flow state. Therefore, it has only one transition temperature, which is the melting point. For low molecular weight polymer materials, it has only two states. One is the static crystalline state, and the other is the dynamic viscous flow state. It is very simple. You only need to consider its melting point. However, for high molecular weight, highly crystalline polymer materials, its melting point is lower than its Tf, viscous flow temperature. In other words, after melting, it enters a high elastic state before transitioning into the viscous flow state. Therefore, its state is more complex. Its transition temperatures are two, the melting point and the viscous flow temperature, corresponding to the curve on the right. Alright, everyone, this concludes our lesson. See you in the next lesson.